Good afternoon. Mark Thompson here for Real Time with IPC. I'm here this afternoon with John Kroonrod from Rogers Corporation, who's actually here to present a couple of papers. The one we're specifically going to be talking about is thermal management. Can you tell us a little bit about that paper, John?
Certainly, yeah. The paper is really based on a lot of experience that we've had from our customers, and it really comes from some confusing items that come in from time to time. And just for example, we may have a customer that has a thermal management issue. They come to us and say, the circuit's heating up more than it should, and why is that? And when we really get in the details, sometimes it's actually not the circuit itself heating up due to the current or the power going through the circuit. It's actually a hot chip sitting on the circuit. And that's kind of a different scenario than actually putting RF power on the circuit and then the circuit heating up because of that. So trying to break that out separately and make sense of each one of them, that's really what the intent is of the paper, is trying to look at the different thermal management scenarios for those two different situations. Of course, you also have the situation where you do have RF power heating a trace going up to a chip that's also heating the circuit. So that's also addressed in the paper as well.
Yeah, I was going to ask you if there are any other implications for that. I mean, are there other situations that affect that?
Right. Yeah, there's actually several things, and I talk about this in the paper. If it's RF power or it's a high frequency type of situation, then you start getting into losses, and you look at losses. In the case of a microstrip transmission line, I talk about the 4 different losses that actually comprise the overall insertion loss, such as dielectric loss, conductor loss, radiation loss, and leakage losses. And from a material standpoint, I really spend more time talking about the dielectric losses and conductor losses, and how that can actually impact the thermal management of it. And really what happens is the more loss you have, the more heat's generated. And as more heat's generated, more problems with thermal management. So the idea there was really just on the high frequency side, microwave, millimeter wave, is to ensure that you understand the losses and then do the thermal management according to loss issues. And you also have things such as our RT Duroid 6035 HTC, which is a very low loss material, so it can be used at very high frequency, but also has very high thermal conductivity. So if you are generating heat due to RF power on the trace, now you have the benefit of the low loss of the material, but you also have the benefit of a material that has high thermal conductivity, which helps the heat flow go through the circuit and to the heat sink.
Typically on what order? You were saying 1.44?
Oh yes, the thermal conductivity for this particular material is 1.44, and that's in a unit of watt per meter K. And most printed circuit board materials, just the standard stuff, is usually around 0.2, 0.25, and then there's some that are ceramic filled around 0.5, and some are a little bit higher, 0.6. But the 1.44 seems to be pretty unique in the industry right now.
Absolutely, that's a factor ahead in thermal management.
Right.
Wow.
Yes, that's pretty significant, we think.
I understand you're also formulating some new materials that are going to be closer to the high T sub G materials that are standard FR4s that are being used.
Right.
And I hate to say that, and I don't want to even use that term FR4s, because clearly this material is nothing close to it in any way.
Yeah.
Tell me a little bit about that.
Sure. It's actually, you're right, it's not really like an FR4 on a molecular level, but we tried to formulate it to where it behaved like FR4 in the fabrication sense. So for drilling and lamination and the fabrication things that the circuit fabricator is going to be interested in, we tried to make sure it really had the properties that would be friendly for circuit fabrication. But it is pretty unique that it's a halogen-free material. It's capable of multiple lamination cycles, sequential lamination, and then also it's very robust for lead-free soldering, and we've had it tested for a variety of different type of applications and configurations. So it seems very thermally robust, it's halogen-free. It's actually a mid-loss material too, and that was targeting some of the high-speed digital applications. So it has a unique combination of properties, and that was our Rogers Theta materials.
Outstanding. Wow. How many layers have you gotten to so far on that?
We've had several different test vehicles built. The most difficult one at this point was a 23 layer that had 2-ounce inner layers, and we had 3 layers of stacked vias. So it was pretty complicated, and we went through sequential lamination to make the build, of course. And then after that, we also went through 10 cycles of 288 degree C solder reflow, looking for delamination or any kind of any kind of negative effect, and we didn't see any. Also looked for a defect called eyebrow cracking, which is something that's kind of unique to buried blind vias sometimes, and that turns out to be a major issue with some of these stacked vias. And it turns out that Theta has not that problem at all when it's been tested accordingly. So we're pretty excited about that.
Can you explain that a little bit? Eyebrow cracking. How does?
Yeah, the
what
eyebrow
is that?
cracking is that's something I haven't been involved with directly, so I'll give you a quick overview as I understand it. But really, what it is it's at the very base of a inner layer buried via, and right at the base of the via, when the defect occurs, it looks just like an eyebrow that curves up into the via. And when it's not there, it just looks like a normal via. You don't see that, but when the defect occurs, it really does look like an eyebrow. And apparently that's one of the defects that they're really struggling with these sequential laminations that have these buried vias. And the theta is very thermally stable, so when you go through these multiple lead-free soldering trials, that's when the eyebrow cracking would occur, but in this case, theta doesn't have that issue. So we're pretty excited about that.
Yeah, I can imagine. This could be a really big thing for the industry.
Yeah, we think so. We're really pretty excited about it. It's also friendly to the fabricator, so it behaves a lot like a standard FR4 when it comes to drilling, speeds and feeds, things like that. De-smear is nothing tricky there, like normal permanganate or plasma is okay, and it's overall pretty friendly to the fabricator.
That's very important. Keeping the chip
definitely.
loads the same.
Exactly.
All of that stuff. So
Yep.
that's outstanding.
Right.
Well, thank you so much.
Yeah, sure. My pleasure.
I've been here this afternoon with John Kroonrod from Rogers. I'm Mark Thompson for Real Time with IPC. Thanks so much.